Hello everyone. We would like to be able to use polar coordinates to do a double integral. So a quick reminder, if I have a circle and I start with the central angle, we have a set of equal ratios, particularly that theta is to the angle all the way around as the area of the sector is to the entire area, which leads us to the area of a sector is simply 1/2 r squared theta. Now that's a handy geometric formula that hopefully most of you remember. Now suppose I have a region in the xy plane but not clearly bounded by y equal f of x or y equal g of x, but bounded instead between angles. So if that angle right there, let's say, was theta 1 and that angle right there was theta 2, then if we said, how do I find the area of this region? What we did was we used the Riemann sum, but instead we split it into little sectors. So each of these pieces would be a sector of a circle. And what we found was, when we did this, we basically integrated this over theta. So the area was the integral from theta 1 to theta 2 of 1/2 r of theta squared d theta. Now this is what we learned in calculus 2. And that's a very practical, very handy formula, and you would use it whenever you had a situation where it would be an easier integral by doing the substitution. Now we want to do it for a double integral. So let's consider the same sector that we did before with the Riemann sum. And what we'd like to do is, instead of just looking at the one sector, we will split it into a bunch of regions. And I would like to find, let's say, the area of that piece right there. Well, if the change in angle we call delta theta I, because this was the ith piece, and then we'll say that this piece right here we'll call the difference between Ri and, Rj and Rj minus 1, then we would have delta Rj, which is Rj minus 1. And so what I'd like to do is figure out what is the area of that piece right there. Well, the easiest way to envision that is not to find a formula specifically for that, but to find a formula that is nothing more than the difference in this area minus this area. Okay? So the bigger area would be 1/2 Rj squared delta theta I. The smaller one would be 1/2 Rj minus 1 squared delta theta I. And if you notice, I can factor out a 1/2 and a delta theta, and let's call this the ijth area. This would give us 1/2 Rj squared Rj minus 1 squared delta theta I. Now notice we have a difference of squares there in the middle. And that then leads to Rj plus Rj minus 1, Rj minus Rj minus 1. So, hopefully you notice, that is delta R, right there. And here, I'm taking half the sum of the R's. That's the average R, which we sometimes will just call R bar. That's the average of the two R's. So we notice if we want to find the area of that piece right there, it's simply going to be of the form R delta theta. So translating that to a double integral now, if I have a situation here where I'm integrating over the region in the xy plane of 1dA, we know this is the area. This will now equal, we'll call it the r theta of r dr d theta, as I take the Riemann sum. Now, what if I have an actual integrand? What if we want to find a volume? So this f of x here, or f of xy I should say, now remember, this notation means you're going to set it up as to whatever's the most convenient, integrating dy dx or dx dy. This integration here would be the same as the double integral in the r theta world, but now this would be f of r theta r dr d theta. Now I'm going to make a separate video with some specific examples, plus there will be examples in the notes. But this is how we convert to polar coordinates.